Welcome, everyone. At Earnin, we have an ambitious goal of automating 80% of all our customer support traffic by the end of the year. And we've made great progress getting there in the last year, but we're not there yet. But before we get to 80%, what would it mean if we automated 100% of all our customer support traffic? How would we know such a system is operating in a compliant way, and how would we make sure that every interaction is creating value for our customers? And how can we surface low-value conversations and hallucinations quickly? We might not have the answer to all these questions, but we want to share with you our journey in building a chatbot and the tools we've used to monitor it and the tools we've had to build to monitor it. My name is Willem Dhaeseleer. I'm here with my colleague, Matteo Ciccozzi, and we're talking about GenAI Observability in customer care. Let's take a quick look at our agenda. We're going to talk a little bit about the complexity of customer support at Earnin. We'll look back at our journey and our timeline, talk a little bit about the metrics we care about when we measure a chatbot. We'll dive a little deeper in the platform we use to emit data to our lake, and we'll do a quick workshop looking into how to query hallucinations on our conversation data by writing a SQL query. And then we'll spend a few minutes looking forward. Let's get started. At Earnin, we believe that we can make any day payday. We're an early wage access company, and we do not require a credit check, or we do not have any interest. Anyone can use our product. We have over 19 million downloads and counting. And with so many users, you can imagine our customer operation is quite substantial as well. In fact, we have over 100 different reasons why a customer might reach out to us for a customer support issue. And we provide 24/7 real-time support directly in our app. And all our traffic, all our support chats go to our bot. Here he is, Earnin. And we're also highly regulated by the CFPB. While we're not a bank, there is a bunch of regulations we have to adhere to. So what that means is not only do we have to provide timely customer care, we have to get it right as well. So this is why last year we started investing in making our customer support even better through GenAI innovation. Let's take a look at our journey. So last year, we released our first version of our bot. In March, we released an FAQ rack-style bot. This was able to answer a single question of a user. The user can initiate a conversation with the bot. We'll try to match their question to an existing knowledge base article from our website, and then we'll use that context to generate a reply. We actually saw relatively low coverage for this initial use case, so we identified a key use case where the bot could help the user update their account. So in June, we released our first tool calling capability, allowing the bot to update the user's account after confirming with the user into a multi-step conversation, a multi-turn conversation. And we saw a massive increase in usage, 500%. So it's really here where we started to realize that our observability tooling wasn't really scaling the way we wanted it. And so we made a decision to emit all metrics directly to the data lake. Before that, we were using Datadog mostly and custom metrics from source code to measure our bot. But what we found really is that even with metrics, logs, and traces, it's not enough to create a comprehensive or a holistic view of how your bot is behaving in production. So in August, we migrated our metric system from Datadog to Databricks. And as we kept adding use cases to our bot, we realized we needed a central place to advertise these metrics, publish these metrics, visualize these metrics. So we released our first AI BI dashboard in October. This really was a game changer, not just because it created a central place for everyone to be aligned on our metrics, but also because it became the operational tool for our bot. So when we push code to production, we're looking at this dashboard to monitor the bot. Keep in mind that this dashboard is backed by Delta Live tables. So the latency or the freshness of the data can be as low as 10 seconds. So that rivals Datadog log ingestion in some cases even. So we're using this dashboard to monitor deployments, do experiments, A/B tests. We've even used it during incidents to quickly scope how many users might be impacted during an outage. In February, we released our first agentic refactor, giving the bot more conversational control over the conversation. And we could not have done this with having all the events stored in the lake. Because in an agentic system, your conversational permutations explode, and it becomes much more harder to isolate the pieces of the conversation you care about from a metric perspective. Then in April, we released our first multi-model capability, where we could take in a screenshot, extract the entities through an LLM, and match it to the correct tool call. And now recently, we're exploring reasoning, to using reasoning models to really diagnose issues across all the data we have in the lake. So to recap here, we migrated our metric system from Datadog to Databricks. So what do we really need from a metric system? Let's talk a bit about that. So we need immediate feedback during experimentation. When we're pushing code to production, we're looking at metrics, and we need to immediately review these conversations as well. These go hand in hand. We also deal with an evolving definition of metrics. Let me give an example of what that means. An easy way to measure a chatbot is in a binary fashion. The bot helped the user, or the bot did not help the user and had to hand it off to a human agent for further help. When you only have what we learned during monitoring and production, however, is that the bot can do useful work before it hands it over to the human agent. So if you learn a new fact like this and you want to incorporate it into your data set after the fact, it can be challenging to do if you only have the time series data. But if you recorded all the events and calculated your metrics on top of the events, you have a little bit more freedom to redefine the metrics as you're measuring them, and you can recalculate them historically or start calculating them without having to push new code. We also deal with high cardinality metrics. So like I mentioned, it's really important for us to be able to break down metrics. And so in Datadog, we can do that by adding a tag to a metric. But this doesn't really scale well with Datadog's pricing model, because Datadog will charge you for each metric for each tag as a separate metric. So it is, and you do not have the same limitation when you are just emitting events to Databricks. Let's talk about the metrics we care about when we measure a bot. We have two metrics that we really care about: containment and coverage. Why do we have two metrics? Because our bot is able to do multiple things. Our bot has multiple capabilities. So we do want to measure each capability individually. So containment is our single use case evaluation. So here we really want to answer questions like, was the bot able to help the customer? Did we contain the conversation, or did we had to hand it over to a human customer agent? And we're also measuring the intent precision here. Like, did we match the question from the user to the correct capability that the bot is able to perform? Coverage is measured over all our customer support traffic. So that means all the capabilities of the bot and all the work that is being done by human agents. This is really our North Star. Like I said in the beginning of the talk, we're aiming for 80% coverage by the end of the year. This is also a measurement of our intent recall, because if we weren't able to measure the intent of the user to the correct capability, we'll lose on coverage. Although that is somewhat more nuanced, sometimes the intent of the user is to talk to a human. So if you have any solutions for that, please, I would love to talk to you after the talk. So containment is really the unit of our measurement. So let's take a closer look at how containment flows through a conversation. The green path here is our happy path. We'll focus on that going from left to right here. So a user can initiate the conversation. We'll try to match them to the correct workflow. And the workflow here is really just a prompt plus tools. If we fail to match them to the correct workflow, then we lose out on coverage. If we are able to match them to the correct workflow, we'll execute the workflow. We'll confirm with the user, did we really resolve your issue? And if they confirm, we'll actually count it as contained. But at any step in this process, the user, the customer, or the agent might decide that they want to escalate it to a human agent, and then we would go through the red path. Or what also happens is users often go away. Like, they might go away even right after we help them. So they might not confirm whether we've resolved their issue with them. In this case, we wait 72 hours to see if they return again before we mark it as contained. This is also a variable number. It's actually a parameter in our AI BI dashboard. Sometimes we look at 12 hours, 24 hours, 72 hours. So how do we get these metrics in the lake? I'll hand it over now to Matteo to talk a little bit more about the platform we've built.
Thank you. So this is a very high-level overview of the customer care architecture at Earnin. So we have Zendesk, which is a third-party service that we basically use as a back-end ticketing system. So when we do have a customer care interaction, we want to keep track of that interaction in tickets, and Zendesk provides that for us. Zendesk's data enters our system via webhook events. So we have webhook events for ticket lifecycle updates. We have ticket events for conversation updates. So imagine messages that a customer either sends or receives. All of these are processed by services running on Kubernetes. They maybe update, process out some kind of internal domain logic, and then publish application events to Kafka. These application events produced to Kafka are consumed by downstream consumers who are interested in these application events. One such consumer is a DLT pipeline, which is part of our materializer capability. It basically consumes these Kafka events and persists them to Delta Lake tables, which are then available to be queried in the lake, of course, with Unity Catalog managing access control. In the case of the chat service, obviously, we also have services that are consuming these events, and one such service, I guess, is kind of the star of the show, our Earnin chatbot, which is a LangGraph application, consumes the event, and tries to assist the customer. So maybe focusing first on kind of this red path highlighted here. So ticket events are stateful events. They carry state. When a customer reaches out maybe for the first time, we want to create a ticket to track this interaction. Once they've been helped, this obviously the lifecycle of the ticket might change to solved. So the ticket service really is responsible for carrying out some domain logic, updating its own domain tables, and publishing to Kafka. The way it does this is by leveraging what the platform offers as an outbox capability, which we'll cover in the following slide. Once these messages are processed by the materializer, which, like I said, is a DLT pipeline, we create an event log table. So the event log table, as the name suggests, is just a simple log of events that are produced to Kafka. Since these are stateful events, events that carry state effectively, we might be also interested in the latest state for a given ticket instance. So effectively, we also have this snapshot table. So the snapshot table is the result of basically applying the events in the event log table in order, and you would end up with the state in the snapshot table. The next flow here in red is, like I mentioned, the chat service. So these are messages that customer sends or receives. These are processed, again, by a Kubernetes service, published to Kafka. And like in the previous case, we also do have the DLT materializer enabled. These are stateless events. So it's just kind of messages, imagine. We only keep an event log table for this. And then, like I mentioned, the star of the show, Earnin, processes these messages, tries to resolve the issue for the customer, and surfaces the response back to Zendesk so that the customer can actually see the response. In the case of Earnin, there's a lot of things that we actually want to persist to the lake. We might care about the trajectory the agent or the chatbot took to assist the customer. What tools did it call? What order did it call them in? So there's a lot of things that we actually want to have in the lake to use for observability. In fact, that's the next step. We have all this data in the lake, which basically creates like an integrated data ecosystem that we can use for various use cases. One such use case is kind of our observability AI BI dashboard. So the cool thing about this is that we can actually query and support, different personas here. You might have engineers who are running like an A/B test or an experiment, and they might be more interested in near real-time metrics, and in some cases also, they might want to spot check some of the tickets. Right, so we have ticket links embedded in the dashboard so that engineers can maybe see, oh, why did this conversation report this kind of behavior, and just look at a conversation as a whole. You might have product personas who maybe are more interested in querying it on like a weekly basis, just to see general trends. Finally, you might also have, obviously, leadership who might be more interested in looking at containment by use case over a larger time frame. So let's dive a bit deeper into the outbox capability, like I mentioned. So the problem is that with the tickets service, right, we process ticket events, and then we effectively need to carry out some sort of domain logic which mutates the service's domain. And at the same time, we want to notify downstream consumers, which are in turn other services, the materializer, and so on, of this state change. So it turns out that to do this reliably is actually not that straightforward, because you might update your database tables, and that you have the transactionality guarantee there, the asset guarantee. But then what happens if you have a partial failure, you don't produce the message? Now you updated your own state, but the other consumers that were interested in these state updates actually don't see that update. So this is where the outbox capability comes in. So the first step is to basically leverage the database's kind of transactional boundary and asset guarantees to make sure that we produce these messages. So when you have an insert, update, or delete to your internal domain tables, you also append an application event to the outbox table. The outbox table is basically like an outgoing mail of sorts, where you publish the events there. And once you commit a transaction, you have a guarantee that your domain tables are updated, and also your outbox table application event has been appended to the outbox table. Then there is the kind of outbox capability. This is a Kafka Connect application, which basically listens to the transaction log of the database and specifically picks out a outbox table events, formats them, and does some other kind of magic there, and then routes to the correct Kafka topic that is configured. So this was publishing. What about materialization? How do we ensure that you can publish in different ways from different sources in different domains, and it just flows through the system and everything gets materialized properly? So this is where having a common message standard, which is basically at Earnin an extension of the cloud events specification, comes into play. So this is the anatomy of a message, a simplified version of the anatomy of a message. We have some headers, and some of the most important ones are mainly the entity ID, which is basically the primary identifier of the instance that you're producing, almost like a primary key. Then you have the entity version, which helps us resolve ordering in this distributed setup. So in the case in which you do process events out of order on the consumer side, you can still resolve the true order that the source intended based on this entity version. Finally, we have the change type. Change type is simply telling downstream consumers, is this like a create event? Are you updating state? Is this a delete event? And such forth. And then the body, that's just the body of the payload, the raw payload. This is where the materializer comes in. So the materializer, like I said, we can imagine a DLT pipeline, which is reading from this Kafka topic, which is the source, and then it consumes this events from Kafka and produces an event log table, or appends to an event log table if one already exists. This is pretty straightforward, just an append-only table. The cool thing is now, in use cases in which you are publishing stateful events and you do want that snapshot table, we can actually create another table that uses the event log as a source and basically applies the changes in order to create the snapshot table. Obviously, in the case in which this has been running, these would just be incremental updates. So this is pretty efficient. However, how do you make this self-serve? Not everybody is experienced or well-versed in Databricks, DLT, Kafka, and there's a lot of hidden complexity, especially when it comes to Kafka and learning DLT APIs. So the idea is, can we make it config-driven? Is there anything really that an engineer needs to know aside from what's my topic that I'm producing to, what's the schema, is this data stateful, and maybe other things around kind of, do you want this run on a schedule, always on, and such forth. So we found that GitHub Actions was actually a good format of automating a lot of this. An engineer comes onto the data platform repository, opens the action, fills in the ingestion template, provides just the information they care about, like I mentioned, topic, schema, and so on, or schema name, so that is then resolved. And then that action, once it runs, creates a PR template that is then reviewed by members of the data team at Earnin. Once that PR is reviewed and everything looks good, we can basically provision that infrastructure, which is the DLT pipeline, effectively. And then this is the next step. For those of you who are familiar with DLT, this is essentially the result. So as an engineer, a backend engineer perhaps, again, who's not familiar from Databricks, you don't need to worry about DLT APIs or whatnot. You just end up with a nice user experience, and you can do custom things like define data quality rules and so on. So to recap, what's the developer experience again? So the first step is you define the contract for your events. We support both protobuf and JSON schema. And these schemas are managed in a schema registry with proper lifecycle management. So schema validation checks when you go to make a change to your schema, making sure we don't introduce any breaking changes. The second step is you publish your events to Kafka. You don't need to use the outbox capability. You can also publish directly in cases where that is appropriate. As long as you adhere to the cloud event specification that we set out at Earnin, you're guaranteed that the materializer will work for your events. Finally, obviously, like I just displayed, the self-serve materialization. So to recap, Delta Live tables, we use Unity for access control, and near real-time option actually enables a lot of use cases. So that's cool and all, but what do we do with all this data? Maybe the best part of this is really having this integrated data environment. So what I mean by this is that we have all the data from all our backend systems that's flowing into the lake, and as long as we can find a way to correlate that with tickets, which is kind of what we operate on in customer care interactions, we can actually add behavior or understand behaviors of the chatbot. So this has turned out to be a really helpful aspect. Needless to say, obviously, notebook exploration also lowers a bit the bar. So anybody can write SQL and kind of slice and dice the data any way they want. Engineers use it to track experiments. The near real-time option is a great capability for that. And also an instant response. It's actually surprisingly helpful, obviously, to be able to kind of dive deep into the data during an incident and understand behaviors. Needless to say, the dashboard does get pretty complicated. There's a lot of SQL queries, and so we wanted to version control this. So how did we do that? Originally, we tried version controlling the SQL queries. That did not work too well. So then we tried, OK, let's use the Databricks version control for the dashboard. And I don't know if any of you have used it, but basically reviewing this lv-json file is not really ergonomic developer experience. So then the next step is basically using asset bundles. But really, the core idea here is treating these queries as kind of assets, because we are using them for observability and monitoring, so making sure that we port over kind of software engineering best practices onto that. I'll pass this now back to Willem.
OK, great. Thank you, Matteo. All right. So we have all our data in the lake, and we find out our bot is not behaving the way we expected. Let's walk through a scenario where we can find the instances this happen. We'll walk through a chat scenario on the left here, and then we'll put the data structures on the right. And we'll try to write this SQL query together here. So let's walk through the expected scenario first. Our user is interacting with our customer support. They want to modify a payment. So the first thing our bot is going to do is going to verify that this payment is currently active and that it can actually help the user. So after it verifies this, the bot will confirm with the user, yes, I can make that change for you. Would you like to make that change? And this is going to be our first question and answer pair, which will represent one row in our table. So this is our table, our chatbot replies table, where we have the user ID, the message of the user, the reply of the chatbot, the tool messages that were called, and the received time. So now we'll generate the second row in our table. The user is going to confirm, yes, please, can you make that change? The chatbot will invoke the tool to actually perform the change. We'll call the modify transaction tool, and the chatbot will confirm with the user, I've made a change for you, and that's the end of our interaction. So this is our second row in our table. But what if the bot hallucinated the confirmation and it didn't actually realize it had to call the tool? This can happen. How can we now find all the instances this happened? When we notice something like this is happening, your first order of business, of course, is to update your prompt or your workflow to ensure it's not happening again. But you also need to look back and find all the cases it did happen, so we can potentially reach out to those users, update their account, make sure that we can meet their expectation. So let's establish conversation context so we can query over these conversations. Because we're able to query over the first row here very easily, we can write a select statement over our chatbot replies. But how can we query the second row? We want to be able to query this row. So we need to query both rows together. So maybe a question for the audience, if we have any SQL experts in the room. How can I get the next row in my result set? Anyone want to try? We don't have a prize, but you'll get the credit. Union, maybe. OK, something else? What's that? Lead, exactly. Yes, the lead function. That's exactly right. So we can use the lead function to get the next result from our user message. And we want to partition it by the user ID and order it by the timestamp. So this way, we have the first message and the second message in our query. And we can do this not just for the message, but also for the reply and the tool messages. So let's put it all together now. We can query over our data. We're going to query our conversation context, and we're going to filter on the first tool call, which is really going to be our anchor point, because we want to find all the times the bot went through this workflow. And we know it went through this workflow if it called this first tool. So we're going to filter for the first tool here. We're just doing a simple string check here to filter over the first tool message. And then we're going to find all the instances where the bot did not perform the actual modification in the next message, which we can do easily by just querying the next tool message. So this will give us almost all our hallucinations. We're missing one more thing here, though. We need to also consider the confirmation of the user. The user said, yes, please, here. If the user had said no, we, of course, also would not have called the tool. So our user here is replying in English. They're saying, yes, please, they might have said something like, okay, or that's great, or they might even have replied in Spanish. We have Spanish users as well. So we need to actually classify the reply of the user as well. And we can do this relatively easy in Databricks as well, using the AI classify function, which is available in Databricks if you're using serverless, and you can easily classify text into two labels here, yes and no. So this way, we are able to query over all our conversations and find all the users that were impacted by this specific hallucination. So this is just one example of how we're using the data in our lake. What we found is that this pattern, using lead, is actually very useful, and it's all over a dashboard. We're not just using it for hallucinations, but we're also using it for, during incidents we've used it, or just categorizing the conversations into different buckets. And you can only do this if you have all your data in the lake, and that's really the takeaway here. Like, make sure your data is available for querying. Okay, I'm going to hand it over now back to Matteo for the rest. Yeah.
So looking forward, what did we learn really with this whole experience? So the first part is what I alluded to earlier, which is how important it is to have this integrated data ecosystem. So it's really easy with, especially when you're developing LangGraph, with LangGraph, it's really easy to focus on that part of the system as it is kind of the most uncertain. But really, when you look at the system as a whole, you realize that there's a lot of potential for leveraging data from other parts of it to kind of perform observability and understand where things went wrong. And in fact, I believe that it's much easier when you look at it from that lens. So really, the importance of having this data ecosystem helped us a lot. The next part is kind of GenAI Observability is a must. Generally, I'd say observability for any service is a must. And to clarify, there's monitoring, which is knowing when something goes wrong, and then there's observability, which is understanding why something went wrong. And in this case, with Earnin and the use cases that the chatbot assists with, there is a very high degree of domain expertise that is required on behalf of the chatbot to assist the user. So it's very important for us to understand the behaviors of the chatbot. When it doesn't behave the way we expect, it's really important for us to understand why. And sometimes this why is very nuanced. So having kind of this observability system in place is very, very important. And as your use cases that you want to onboard onto the chatbot become more complex, the observability needs to grow in parallel with it. Finally, the importance of quick feedback cycles. So this is also a sort of a standard practice, and in traditional software engineering, maybe even things like unit tests that you can step through locally to understand how things work. So having all this data into the lake allows us to basically achieve something like this, which allows us to review chatbot behavior, measure things that we want more of or less of, and then iterate on it. So where to next? Like Willem just showed an example of how we leverage this data for hallucination detection, essentially. So the idea is like, let's try to do this in a proactive fashion. We're streaming all this data. There is an opportunity for us to actually be able to catch issues like that in near real time and proactively address those for the user. Use case discovery. So this is also a big one. We have all this data in the lake, and like I said, there's a lot of domain expertise that is required. We have also all the human agent support chats in the lake. So can we leverage all the cases where the chatbot maybe was not able to assist the customer, and then this was handed off to a human agent? Can we learn from all this data, and can we use this to build a large offline evaluation set that covers use cases that we don't know about also, not only the use cases that we do know about? Finally, model improvements. Can we use data, again, from human agents to improve the chatbot in more intelligent ways, ways that will allow us to expand our use cases without knowing what the specific use case is beforehand? So these are three key pillars that we're hoping to expand into next. With that, thank you for attending. Please do complete your surveys on this section, and that's all.
Yeah, we ended a bit early, but we have time for questions if anyone has questions. Oh, thanks.